Welcome, everyone. Today, we are diving into one of the most fascinating and practical topics in mathematical physics: non-homogeneous, second-order ordinary differential equations. If you have ever wondered how buildings survive earthquakes or how radios tune into a specific frequency, you are in the right place. Let us get started. Let us begin by building our intuition. Imagine you are sitting on a playground swing. If you pull it back and let go, it swings naturally until friction stops it. In mathematics, this isolated, unforced motion is what we call a homogeneous system. But now, imagine a friend stands behind you and gives you a push every time you swing backward. You are no longer just moving on your own. You are being forced to move by an outside push. This external driving force is exactly what makes an equation non-homogeneous. We are going to study systems that are actively driven by these outside forces. Now that we have a feel for the physics, let us look at the formal definition. A non-homogeneous, second-order, linear ordinary differential equation is one where the derivatives of our unknown function are set equal to a non-zero function. Remember, in a homogeneous equation, the right side is always zero, which represents a closed, isolated system. But here, that right side is a specific mathematical expression called the forcing function, or driving term. This means the overall behavior we observe is a tug of war. It is dictated both by the system's own internal physical properties and by this continuous external push. Why do we care so deeply about this mathematical distinction? Because in the real world, almost nothing is completely isolated from its environment. Engineers and physicists rely on these exact equations every single day. When you drive over a bumpy road, the bumps act as an external force, and the car's suspension must be designed to respond safely. Electrical engineers use these equations to analyze circuits driven by an alternating current power source. Without a deep understanding of non-homogeneous equations, we could never predict how tall skyscrapers would react to the violent shaking of an earthquake, or how suspension bridges would sway in heavy winds. This brings us to the mathematical representation. Here is the standard blueprint for all the physical systems we just discussed. On the left side, the variable y represents the unknown function we want to find, like the position of a mass. The constants a, b, and c represent the internal physical properties of the system, such as mass, friction, and spring stiffness. But the crucial part is on the right side, f of x. This is the external forcing function that makes the equation non-homogeneous. If the magnitude of f of x increases, the external push on the system becomes stronger, resulting in a much more violent forced response. Our job is to solve this entire equation. To solve this equation, we cannot just find one single piece of the puzzle. We must construct a general solution that accounts for both the inside and the outside of the system. This formula tells us exactly how to build that complete answer. The total solution, y of x, is made of two parts. The first part is y sub c, called the complementary function. This represents the natural, unforced behavior of the system, as if the external force was zero. The second part is y sub p, called the particular integral. This is the specific mathematical solution that satisfies the external force. To get the full picture of how the system behaves, we simply add the natural response and the forced response together. Now that we know the solution has two parts, let us outline our strategy for finding them. We will always follow a two-step process. First, We temporarily ignore the right side of the equation. We pretend the external force is 0 and solve the homogeneous equation to find our complementary function. Second, we look at the actual forcing function and make an intelligent guess about how the system will respond. This technique is called the method of undetermined coefficients. We guess the shape of the particular integral, plug it into the equation, and solve for the missing numbers. Finally, we add our natural solution and our forced solution together to complete the problem. Before we move on, let us see this strategy in action with a concrete example. We want to solve y double prime minus 3y prime plus 2y equals e to the power of 3x. First, we find the homogeneous solution. The characteristic equation gives us roots of 1 and 2, so our complementary function is c1 e to the x plus c2 e to the 2x. Next, because our forcing function is an exponential, we guess that our particular integral will look like a times e to the 3x. We take its first and second derivatives and substitute them back into the original equation. Simplifying the left side leaves us with 2a e to the 3x equals e to the 3x. Dividing both sides shows that a equals 1/2. Finally, we add our complementary and particular solutions together to get our final answer. So we have successfully solved the equation, but what does this final answer actually mean physically? The equation tells us that the system's total behavior is a combination of its natural exponential growth and the specific exponential growth forced upon it by the external source. The natural terms, with the arbitrary constants, depend on how the system was initially started. However, look at the exponents. The natural growth has exponents of 1 and 2, but the force term has an exponent of 3. This means that as our variable x increases, the force term will grow much faster than the natural terms. Eventually, the external push completely dominates the behavior of the system. Now let us tackle a system with a sinusoidal forcing function, like an undamped harmonic oscillator being rhythmically pushed. Our equation is y double prime plus 4y equals 3 sine x. Solving the homogeneous part gives imaginary roots of plus and minus 2i, which translates to natural oscillations of cosine 2x and sine 2x. For the particular integral, since the force is a sine wave, we must guess a combination of both sine and cosine. We find the second derivative of our guess and substitute it into the original equation. Grouping the cosine and sine terms together gives us a simple algebraic comparison. Matching the coefficients on both sides reveals that a is 0 and b is 1. Adding this to our natural response gives us our final complete wave equation. Let us pause and understand the physical reality of this new solution. This mathematical expression perfectly represents a mass hanging on a spring with no air resistance. The complementary function tells us that the system naturally wants to bounce at an internal angular frequency of 2. However, the particular integral shows that the external force is simultaneously making it bounce at a frequency of 1. The actual physical motion you would observe is not just one simple wave. It is a complex, beautiful combination of both these rhythms happening at the exact same time, pushing and pulling against each other. To truly grasp this, let us look at a visual representation of these combined motions over time. On this graph, the horizontal axis is time, and the vertical axis is displacement. Notice the dashed blue line. This is our complementary function, often called the transient solution, because in real systems with friction, it eventually dies out. The dotted red line is our particular integral, the steady-state forced response that keeps going as long as the external push continues. Finally, look at the thick purple line. This is our total general solution. Early on, the motion is complex and irregular because both the natural and forced rheos are active. But as time goes on and the natural response fades, the total motion perfectly aligns with the external driving force. We have covered a lot of ground today, so let us summarize our key takeaways. First, non-homogeneous differential equations are the essential mathematical tools we use to model physical systems driven by external forces. Second, remember that the complete solution to these problems always comes in two distinct, equally important parts. You must find the complementary function to understand what the system naturally wants to do, and you must find the particular integral to see how it is forced to behave. By adding these two pieces together, you unlock the complete real-world picture of the system's dynamics. You now have the framework to predict the behavior of everything from simple pendulums to complex electrical grids. Great work today.